So, right. So we're talking about the tangent space to the tangent bundle. So we've taken a point PV, we're calling that theta, which is a element of the tangent bundle. And then we're looking at a curve alpha, which is passing through the point PV at time 0. And so the curve alpha of t, it will be given by what? It will be given by a curve in the base in M together with a vector field along the curve gamma, right? Okay. And so we want to understand this tangent vector alpha prime 0. So by definition, if I call this xi, this is an element of t theta tm, right? The tangent space to tm at the point theta. Now what I'm trying to do is break up this infinite. So this xi you think of as an infinitesimal change in theta, right? And changes in theta I can break up into a change in the foot of theta and a change in the head of theta. So the change in the foot will be just the derivative of this curve gamma at 0, gamma prime 0. So that is d dt at t equal to 0 of gamma t. Gamma t is nothing but pi of alpha t, where pi is the canonical projection from Tm to n, which sends a tangent vector to its foot. And by the chain rule, d dt at t equal to 0 of pi of alpha t, this is d pi at theta, d pi at alpha 0 of alpha prime 0. So that is d pi theta of xi. Is this clear? Yes?
Yes.
Okay, so the change in the foot is nothing but d pi theta of xi. Right, remember where is pi goes from Tm to m. So d pi theta, where will it go from? D pi theta will go from t theta tm to tpn, right? Okay, so this is the change in the foot. This is an element of tpm. Is this clear? Yes? Any question? Any question? Okay, so now let's look at the change in the head. So what is the change in the head? So it's going to be basically, I look at this change in the head, I divide by t and I let t tend to 0, right? So I can write this as limit t tends to 0. So this will be w minus ptv. So that's zt minus ptv divided by t, right? Okay. Yes. Now what is zt? If I write zt with respect to a parallel frame along gamma, I can write this as summation ai of t, ei of t, where ei's are parallel vector fields along gamma. Right, I have a basis of parallel vector fields along gamma, and any vector field along gamma I can write as a linear combination of them with coefficients which are smooth functions. Okay. So in that case, what is Z0? Z0 is V. Z0 is V, and Z0 is summation AI0 EI0. So this will be limit t tends to 0. Sum over I. So zt will be ai of t. And what will PTV be? So PTV, so V is equal to Z0, which is summation AI0, EI0. So what will PTV be? Anyone? What will PTV be? This will be a linear combination of the EITs, right? But the EITs are parallel, so that means the coefficients of PTV have to be constant, right? With respect to, so these will just be AI0, EIT, right? So this will be nothing but AIT minus AI0 divided by T into EIT. Okay. Now as T tends to 0, this AIT minus AI0 by T, this tends to AI prime 0. And EIT tends to EI0. So this gives me AI prime 0 summation over I, AI prime 0, EI0, which is exactly Z prime 0, right? So this is DZT dt at 0, right? Yes, the covariant derivative of Z along the curve gamma at 0. Is this clear?
Yes.
So this is also an element of T. Okay. All right. So is this clear?
Yes. Yes.
This will be the infinitesimal change in the head. It's just the covariant derivative of the vector field along gamma at time 0. Right? That is the change in the head. Okay, and the change in the foot is d pi theta of xi. So this change in the head, this leads us to define a map called the connection map. So this leads us to define a map called the connection map. So theta equal to PV in TPM. Then the connection map K theta. So this will go from T theta TM to TPM. This is defined as follows. So let xi be an element of T theta Tn. Okay. So then you choose any curve alpha from minus epsilon epsilon to Tm such that alpha 0 is theta and alpha prime 0 is xi. Okay. Then you write alpha t as a curve gamma t, comma, a vector field zt. Okay. So where gamma is a curve in M, a smooth curve in M, and Z is a vector field along gamma. Okay. So then we define the connection map by k theta of xi. This is defined to be capital D dt z at 0. Okay. So the covariant derivative of the vector field z along gamma at time 0. Okay. So that's what would be the change in the head, right? That's what we found from this calculation above. The infinitesimal change in the head is dz dt at 0, right? So that's why that motivates this definition, all right, of the connection map. So first thing to check is that this is well defined, right? Because here we're choosing some curve alpha so that alpha 0 is theta and alpha prime 0 is xi. So there are infinitely many such curves, right? So we have to check this is independent of the choice of curve alpha, right? And the second thing is to check that this is a linear map between these vector spaces, right? Okay, so lemma k theta from t theta tm. So note this is an element of TPM. So from t theta tm to TPM is well defined and linear. Okay. So proof. So let x equal to x1 to xn be coordinates near P, and let x1 to xn y1 to yn from Tu subset of Tm to Rn cross Rn be the corresponding coordinates on Tu. Okay. All right. So let this pair xy composed with alpha t. So this becomes a curve in R2n. So I can write this as some tuple of 2n functions, x1t, xnt, y1t, ynt. Okay. And so if alpha t is equal to gamma t zt in Tm, then x of gamma t is equal to x1t up to xnt, and y of so, and maybe I should write it this way. Zt is equal to sum over k yk of t del del xk, right? This is how the coordinates yk are defined. Okay, so up to here is all right? Yes?
Yes.
Okay, fine. So now what is alpha prime 0? Alpha prime 0 equal to xi. This is equal to sum over k xk prime 0 del del xk plus yk prime 0 del del yk, right? Okay, so this is an element of t theta tm. Yes? Okay. Yes? Yes? All right.
Yes. Yes. All right.
Now, what is the connection map? We're defining it to be dz dt of at 0, right? So this we know what it is. This covariant derivative is the usual derivative, sum over k yk prime 0 plus sum over ij d xi dt at 0 into gamma ij k yj at 0, the whole thing del del xk, right? Yes, we have this formula for the covariant derivative. It's the usual derivative plus a correction term coming from the Christoffel symbols, right? Yes?
Yes.
Now, what is yj0? So I should say here that so zt is equal to summation yk t del del xk. That means z0, that is v. This is summation yk0 del del xk, right? So this d dxt ddt of xi at 0, this is just xi prime 0. So let me just write xi prime 0 here. So this thing, what you can see, this only depends on the vector x1 prime 0 up to xn prime 0 and y1 prime 0 up to yn prime 0, and on the vector y1 0 up to yn 0, right? Yes? And
Yes.
this x1 prime 0 to xn prime 0, y1 prime 0 to yn prime 0, these are just the coefficients of xi with respect to the basis del del xk, del del yk of t theta tm. So therefore, this only, and y1 0 to yn 0, these are the coefficients of the vector v in TPM with respect to the basis del del xk. So therefore, this only depends on your theta and xi, right? Hence, only depends on theta and xi. Is this clear? Yes. Therefore, this is well defined,
Yes, sir.
right? So k theta is well defined. And k theta is linear because this above expression for dzt dt at 0, this is linear in the variables x1 prime 0, xn prime 0, and y1 prime 0, yn prime 0, right? It is linear in these variables, right? Because it is linear, because dz dt at 0 is linear in x1 prime 0, xn prime 0, and y1 prime 0, yn prime 0. Okay. Is this clear? So that finishes the proof of the lemma. Is this all right? Yes?
Yes, this is all right. Yes.
So now what do we want to show? Now we've defined the change in the foot and the change in the head. And so what we want is to prove the following theorem. If I look at the pair d pi theta comma, so let me call this j sub theta. This is the pair d pi theta k theta. So this will go from t theta tm to TPM direct sum TPM, where the first entry is the change in the foot. The second entry is the change in the head. This is a linear map. We want to say that this is an isomorphism. Okay, we want to say that this is an isomorphism. Is this clear? Yes? Okay. Is the statement clear?
Yes, sir.
Okay, so now we can come to the notes, having motivated this. So basically this, this map is xi maps to d pi theta xi k theta xi. Okay. So this is proved in the note. So let's move to the notes. And maybe we won't finish today, but let's do part of this. So, all right. So geometry of the tangent bundle. So we have our Riemannian manifold M, and we have Tm is the tangent bundle, and pi is from Tm to M is the canonical projection. So now we can define what's called the vertical subbundle of TTM. So this will be a subbundle of TTM. Remember, TTM is a vector bundle over Tm, right? The fibers are the tangent spaces T theta Tm. So what we're going to look at is in each fiber, I look at the kernel of d pi theta. So I've written it as d theta pi, but it should be d pi theta. Okay. So the kernel of d pi theta, this is a subspace of T theta Tm, right? This is a subspace of T theta Tm. So I want to say that this is of dimension n. This is half the dimension of the total tangent space, which is 2n. All right. So, the picture is that, so what's the picture? So, V theta is defined to be the kernel of d pi theta from T theta Tm to Tpn. So this is a subspace of T theta Tn. So what does it mean to be in the kernel of d pi theta? That means the foot is not moving. You're only moving your head, right? So you're standing still and your head is moving, not your foot. You're standing in the same spot and you're moving your head, right? So what would that be? That be one way to get such an element of this V theta is basically you take V and then you take any tangent vector in TPM and you look at V plus TW, right? Where W belongs to TPM, you can add these two vectors, they're in the same tangent space. So then the foot is constant. So if I differentiate this curve, right? Then, so let me take a W in TPM. Then let me define a map, sigma W, So, I mean, let me define a curve. Sigma W of t is V plus TW in TPM. Okay. So pi of sigma W. So, I mean, okay, fine. So to be more precise, let me make this P comma V plus TW in TM. Okay. So then sigma W 0 is equal to PV, which is my theta. And pi of sigma WT, this is constant equal to P. That means that ddt at t equal to 0 of pi of sigma WT, this is equal to d pi theta of sigma W prime 0. This is equal to 0, right? Because this curve pi of sigma WT is constant, so its derivative is 0. So what does that mean? That means that sigma W prime t, sigma W prime 0, this is in the kernel of d pi theta, right? This belongs to kernel of d pi theta. Which is v theta. Okay. Yes.
Yes.
All right. Okay. Now we have the following lemma. The map. So let me just call it phi from TPM to v theta. W maps to sigma W prime 0 is linear and an isomorphism. So this is a linear isomorphism. Okay. All right. So this vertical fiber v theta, this is identified with TPM. Okay. This is isomorphic to TPM. So proof is well, one way to prove this is just by taking coordinates. So let x, y from TU to Rn cross Rn be coordinates on TU, and let P1 from Rn cross Rn to Rn and P2 Rn cross Rn to Rn be the two projections onto first and second factor, be projections to first and second factor. So so if let's say V is equal, so theta is equal to PV, and V is equal to sum over I say AI del del xi, and if I take a W in TPM, W is equal to sum over I BI del del xi. Okay. So then sigma W if I look at so let me call this coordinate, let me call it phi. Okay, so then capital phi of sigma W of T okay, so let x of P be some say P1 to Pn. So capital phi of sigma Wt will be what? It will be P1 to Pn. And then A1 plus TB1 up to AN plus TBN. So let's end this meeting and we'll just do another 10 minutes and finish this. Okay. So let's end this meeting now.